brief review. We started off with foundations of crystallography. We're going to continue with crystallography. We've gone over crystal classes, Bravais lattices, and crystal systems, Bravais lattices, and crystal classes, and then the 230 space groups. This is where we left off for sake of time. We went over the international tables of crystallography and its use. There's a lot of information in the international tables, and it's always updated. Well, there's a 2006 version and the 2016 version. The 2006 version, I'll reemphasize, is what we have access to, and that's fine. The majority of crystal structures are there. I believe the update is really the e-glide. So anyway, it's packed full of information, and I would say it goes really into the depths of crystallography and the mathematics of crystallography. So you can really spend a lot of time just really diving into the syntax and really, the mathematics of the construct of what crystallography is. For the purposes of this class, I will point you to the resource. And what's really good about international tables is, of course, it gives us all a common language to describe crystal structure as a starting point. And it also has all the definitions. So there's a lot of terminology of which, and a lot of symbols that we went through that honestly, you don't have to really commit to memory because there are tables here for you as a reference, so it's quite useful for that purpose. Okay, I see what's happening. So one moment, and I get the handy dandy. So I guess I could advance this way, be a little bit faster. All right. So to get, we've discussed some of the symmetry elements. Last time I re-recorded a nice summary because yours truly forgot to hit record. So hopefully you enjoyed the 12-minute summary recording as opposed to our wonderful, lovely 55-minute discussion that occurred. So there are some things that are missing. So now today we'll continue with screw axes and glide planes to go from the 32 crystal classes to 230 space groups. So here, the notation, when you see these notations here, when you see a number and then a subscript to remind you all, that's indicative of a screw axis. And it's quite straightforward. So if you see the larger number, I denote that here as capital A. And then if you see the subscript, generically, that's subscript B. All that means is that you're going to perform an A fold rotation. So in the underlying example here, 2 sub 1, that means you're doing a 2-fold rotation. You're rotating by 180 degrees. And then you follow that by a translation of the ratio of B divided by A along that axis. So if you have a screw axis along A direction, B direction, C direction, depending on where the notation is in the space group notation, that's what you do. So here you see the 2-1 screw axis is along this way. So you rotate by 180 degrees and then translate. So you rotate by 180 degrees along Z, which is here. And so the plus and the minus tell you that it's above or below the plane or the page in this case. And then since it's 2 sub 1, it's 1 divided by 2 translation along direction of the Z axis. Okay, so you do this for any number of the representations here: 3, 1, 3, 2, 4, 1, 4, 2, and so on, so forth. So 6, 3 means you're translating by the same amount, by half a cell, 3/6, or 1/6 of is 6, 1. So that's pretty straightforward, I hope. And then the glide planes. So you see this a lot in you know, when you see notations such as A, B, C, and also N, D, and E in the 2016 International Tables of Crystallography, and all that tells you is now you're going to combine a mirror plane with translation, okay? And the denotation is if it's A, then the glide planes are parallel with that direction. So if it's A, then it's parallel to the A, typically that's X, and then B, C. So how you define A, B, C, that will be given in the symmetry, in the space group. If you're, so here's an example. So in the solid state chemistry textbook, they have something like this, which I find somewhat helpful, but I think a more helpful representation is a 3D example. So if you had, let's say, this rectangular prism, and you had, let's say, an A glide. So that means here's the plane, right? Here's the glide direction. And so if, let's say, your point is here, I denote that as this letter A, so that, you know, there's some asymmetry, so it's easier to visualize than just a dot. So what you do is then you, right, oops, excuse me, sorry about that. Right, so, oh, oops, sorry. So used to writing the correct way, right? So you mirror the letter A, and then you translate that, right? So here, that's the translation is the standard half of a unit cell, unless it's an N glide, in which case then it's both in A and B, then you translate by half of the cell, or if it's a special D glide, which you see in lithium manganese oxide, there's a D glide in there, FD bar 3M, that means you translate in A and B, or well, since D is the first letter, then it's A plus B, but then you translate by only a quarter. So all of this is just to say, these are standard notations that you don't have to commit to memory. It is useful to commit it to memory for the space groups that you often work with the materials that you often work with, but you can look all of this up. And in fact, I would say if there's a reference book, use a reference book, right? But this allows you to be able to read space groups when you see things like, oh, lithium manganese oxide. Okay, well, if it's FD bar 3M, I know you should be able to backtrack what the point group is and what kind of symmetries it will have. And that spells out then for you where the atoms are and where the vacancies will also be based on the multiplicity. Okay, so that the E glide is the biggest change in the 2016 version. Okay, so that means then once we now have the crystal system that we talked about and the inversion symmetries and all the symmetry elements as well, we can then map out all the 230 space groups that are coupled together. And then, you know, when you see specialized notations like, you know, face-centered cubic, instead of just saying face-centered cubic, we have a particular name for it because it's a very special symmetry. And a lot of the metals that we're interested in have face-centered cubic, so we, you know, have a particular name, face-centered cubic for it. But really it's just space group, you know, 225 FM bar 3M, right? So we understand the crystal structure of FM bar 3M, face-centered cubic, then we can also then parlay that to understanding the properties of other face-centered cubic systems. And so when you see, it's F, that means there's, the atoms are on the faces, right? And there's M, there's a mirror plane. And then bar 3, there's a threefold rotation along the, because it's cubic, along the 111 direction. With inversion, it's bar 3, and then a mirror along the 110 face diagonal. Right, so when you see something like that, that's what it says to you. And you can do that for all space groups once you see the notation, right? Okay, so why does it matter so much to know these notations, and be able to communicate with them is because when someone says a certain space to you, you can automatically start to classify and understand certain physical properties without doing an experiment. Now, right now that we have done some experiments, now that we've done some computations, and we understand how properties of materials relate to that of the crystal structure of those materials, we understand how the properties arise. So I gave some examples here just so we're not so narrowly focused on energy storage materials design, even though that is the point of this class. So I gave some examples here that are related to other energy materials. So if you look at here, if you start off with the 32 point groups, then you can look at the symmetries and you can say, okay, well, how many of them are non-centrosymmetric? That means they don't have the inversion. Why does that matter so much? Well, that matters because let's say I have the example here of piezoelectricity, right? So this particular space group, well, lead titanate is sort of the archetypical material of what a ferroelectric, piezoelectric material can be. But in the cubic phase, the lead atom is, are at the corners here. So those are the gray atoms, and titanium in blue, also represented by the blue polyhedron that's here. Titanium will sit at the center here, and the oxygen atoms are in red. So in the cubic phase, it's all symmetric, right? But then in the tetragonal phase, when the titanium is a little bit off center, this is where the world of ferroelectricity, piezoelectricity, this is where the physical properties come into play. And this is where, those who study perovskite, this is a very well studied system. It goes back of many, many decades of people trying to understand the crystal structure, the average crystal structure, as well as the local crystal structure, and how that has an effect on the physical properties, right? So the fact that the titanium atom moves off center allows us to take advantage of its property of generating electricity from pressure or heat. So the example that are often in textbooks are like barbecue lighters. There's a crystal in there, and it's usually actually PZT. There's a little bit of zirconia doped in, but when you click the little button, you're applying some pressure that generates a voltage, and that voltage difference sparks the gas that's in there, and thus your lighter lights up, right? So and that is all because of the PZT crystal structure. That's all because the titanium and zirconium are off center a little bit, right? And that wouldn't happen in the cubic phase. So just communicating a material like PZT, or which is lead, zirconium, titanium oxide here, lead titanate, zirconate titanate. Just communicating that the material is PZT, or just communicating that it's lead titanate, right, is not at all telling you the majority of the story, right? What really tells you and communicates the possibilities and also what to expect of the physical properties is through communication of the crystal structure, right? If you said PZT or lead titanate, but cubic, that's not so interesting. But once you start communicating that it's tetragonal, right, then you know which way you should orient the crystal to maximize the poling and also to maximize the electric effect based on the pressure that you apply, right? So that has huge implications that way. Ferroelectricity, also a property that people try to take advantage quite a bit. There are a lot of ferroelectric materials out there. It's a very old, as in it's been studied for a long time, but I chose this particular material because for an energy storage materials class, lithium niobate is one of the most discussed materials as a coating material. right, to protect cathode materials from decomposition at the interface with the solid electrolyte. And so you increase cycle life that way. But interestingly, not only is it a good coating material, but it also has really interesting ferroelectric behavior. So if you understand its crystal structure, you don't just have to use lithium niobate, you know, in as a coating material. It has far-reaching uses in applications for ferroelectricity. And what that means is that you can generate electric polarization. So basically, an electric field, electric polarization that can be reversed by the electric field. And it has a huge band gap for EV. That's relatively huge. Titania is like 3.5 EV. That's already huge. That's the scale of things anyway. Although now there's also 5 EV band gap material. So it's all relative, you know, what is huge and what application you're using it for. But it's because it can generate, you know, electricity, this electric polarization, it's also used as a good material for as a photo detector. So beyond just a good coating material for, you know, for cathodes and increasing cycle life. Okay. So I had some slides in here for discussing crystal planes, syntax, nomenclature, how you derive, you know, you see a picture of a crystal plane, how you can obtain the name, you know, the Miller index of the crystal plane, and also crystal direction. This is something that material science, this is at the core of material science and engineering, but I know in our audience, not everyone has that background. So I give you the option, we can go over it if people want to. If not, we can just bypass it. That's not a problem. As I've said, this class is adaptable. So if you've taken a look at the slides and you feel pretty comfortable, then, you know, I don't want to belabor the point and make review too elementary for folks. Wait, this time is confusing, David, because it's either you're good on Miller indices. Okay, that's one vote. There are 3, 5, 6 of you today. We've lost some due to the snowstorm, so it's democratic, so, well, within bounds, right? So, okay, so there's a vote on going through it, so 1-1. Any other opinions? Because we're at a dead tie, so. All right, David has acquiesced. It'll be good review for you, David, if you feel comfortable with it. Or rather, David, you're welcome to lead us through it because it's all outlined right here. So, you know, you want to go through it, David?
Sure. What I remember, when I look with a plane, it's got 3 different axes.
Mm-hmm.
So it looks like this one doesn't intersect the.
Okay.
That one.
Yeah. That's true. First, define your axes is probably the most important point. Yep.
And of course, y-axis basically you have one of our.
Mm-hmm.
1, 1, infinity makes infinity and not 0. Actually, something is 0, not something at all.
Mm-hmm.
Say. That we had as like 0.
Mm-hmm. Okay. Thank you, David. That was a very thorough summary. So I'll just briefly go over, mainly because I don't think the Zoom folks, I think there's actually one Zoom person can hear you, but also just to make sure that I go through it, specifically as well. So that was a great summary. I would say that's a good summary and a good approach. This is the systematic way of doing it. If you're ever unsure, you just go 1 through 6, and that should get you to the Miller index. And since it's a plane, we use the regular parentheses, whereas a family of planes, right? We can use the curly brackets. And I just want to emphasize, just to make sure we're definitely all on the same page, right? David mentioned about the infinity. I want to just point out that because this is the 110, this particular example was chosen so that we address what happens when the plane does not intercept the one of the axes or two of the axes, right? So here, right, if you look at the intercept, if you choose the origin, well, first of all, you have to choose the origin. The most logical selection would be 0, 0, 0. But since this particular plane does not intersect 0, 0, 0 at any point, it's denoted as infinity C. So that's why when you take the reciprocal 1 over infinity, that's how you generate 0. Okay. So I just summarized David because I didn't want to go through explicitly again. But so was that sufficient, or should we do another example, or I just go through it and bypass David? Oh, well, first you have to know where, so your unit vectors are A, B, and C. So in addition, okay, thank you for pointing that out. So in addition to denoting what your axes are, this is an arbitrary unit cell, but in X, I'll call the unit vectors A, B, and C. Right? So basically those are your lattice parameters. So then you need to know, where does your plane intercept X, Y, and Z? Well, here you go 1A, here you go 1B, but because in the Z direction, there is no intercept. We say, well, that is by definition in an infinity. Mathematically, it's infinity of C, and then when you divide 1 by infinity, you get 0 by definition. Okay. Here's another example. I chose this example to show you the exception, not the exception, sorry, another technique where if your plane goes through the origin or touches your origin of choice. So here, the origin was selected as 0, 0, 0. In this case, you then move your origin. So that's another technique. You move the origin. So I just moved the origin from 0, 0, 0 to now 0, 0, 1. Okay. So now everything is within the frame of reference of where this is now origin. Okay. This is X, this is Y, this is Z. Unit vectors are still with distance A, B, and C. So then the intercept will be 1A, 1B, and then because this is your new origin, you actually had to go down -1C. So that's how I got to -1C for intercept. Then you take the reciprocal, so 1 over 1A is 1 over A, 1 over 1B is 1 over B, 1 over bar 1, sorry, -1C. 1 over that is -1 over C. You normalize everything. So you divide out by A, B, and C, and then you reduce to integers. So that's what David mentioned. If these numbers were not integers, they were fractions, you would then reduce to nice whole integers, and you would say this is the 1, 1, bar 1. And that's how you would say it, bar 1. The bar comes first. Okay. And then if it's a family of these, so that means you're saying, this is an arbitrary unit cell, right? But let's say it's cubic, in which case then you're telling me 1, 1, bar 1 is equivalent to 1, bar 1 is equivalent to bar 1, 1, 1. Okay, so hopefully that was good review for everyone. Obviously I went through it fast because I read the room and it seems like we just needed a brief review. But if you really wanted to sit down and slow everything down and maybe work with some more random, numbers or arbitrary numbers, more complex planes and such, I have examples that are uploaded to in very short videos, like 2 to 3 minutes, where I just go through each example separately. So that way you can watch one video, you can watch 4 videos, but you can, pick your own adventure, given the amount, depending on the amount of time you have or the amount of content that you want to review. Okay, crystallographic directions. This is the most common way of determining crystallographic direction. It's called the head-tail method. There are different ways that people do it, but the head-tail methodology is outlined here, where one, you choose your origin. So if you had to draw, or if you're given, let's say, the direction, the way you determine the crystal direction is one, you choose an origin. So here I can see, okay, well, it doesn't pass through the zero, it doesn't pass through 0, 0, 0. So I'm going to make that my origin. Then you pick, what you look at where the head is. Well, once again, we need to define our axes and the lattice parameters. So unit vectors A, B, and C, that's the distance. So the head here will intercept at 0A, because we didn't go anywhere in this direction. So here, this point is 0A, 1 in B, and half in C. The tail, we went 1A in the X direction, 0 in B, 0 in C. We take the difference, and then once again, we convert everything to nice integers. So here you see if the difference is, -1, 1/2, simple enough to multiply everything by 2 to get us the, 2 bar 2, oh, sorry. Bar 2 to 1 direction. So it's really just a difference, right? It's just vectors. That's all it is. But now you have the complexity of like the lattice parameters in there, but that's it. So I have an additional video, so as to not belabor the point so much, of drawing, if you're asked to draw 1 bar 1 0, that's uploaded to the media site channel for you to review and practice if you wish. Okay. All right, so now we come back to our discussion last time, where we talked about graphite as a material for and its crystal structure. So we talked about its crystal structure, P63 over MMC. Right. So now when you look at the space group, you see 6,3. It has to be hexagonal and it's primitive, which means one of the atoms is going to be at the corner. So that has to be 0, 0, 0. Right. So already our discussion crystal structure gives you an idea of what this material is going to look like. And in reviewing our discussions from last time, right, we discussed as a group why lithium ion or this material would be more useful for lithium ion insertion and deinsertion than, let's say, for sodium ion. And as a group, we decided, well, it's a layered material, but the van der Waals layer is not big enough, right? So that was the overarching superficial statement of its crystal structure. Now we can actually drill down and say, well, what about its crystal structure makes it useful for fast kinetics for lithium ion insertion and deinsertion? Well, here we look at the lattice parameters, A, B. So the basal plane, the lattice vectors have to be equal to each other. So A and B are 2.464. C is 6.711 angstrom. because it's hexagonal, the gamma has to be 120 degrees. So we've mapped it out. So here, if we look down the C-axis, okay, we see the honeycomb structure. If we look, from the side here, we see, okay, so here's a van der Waals layer. So that confirms, what we discussed already as a group. But then we look specifically into what this spacing actually is, which is 3.4 angstrom. And then we can look up the ionic radius of lithium as well as of sodium. So not the metal, but the ion itself. And we look at, well, the charge for a coordination number of 6. And how do we know it's 6? Sorry?
It's also size.
Yes. Yeah, the coordination number, yes, is related to the size, but you can have different coordination numbers for lithium. Yeah, so
For a given atom in this structure.
yes. So the punchline is look at the crystal structure, open the crystallographic information file and just look at the crystal structure. Granted, this is hexagonal. This is, P63 over MMC. So one of the more common crystal structures, this is a crystal structure that you probably learn in Gen Chem and Intro to Material Science. So, so you would know about its coordination number there. But if it were something that's not covered in like a general course, you could just go and look up, the crystal structure and open up a visualization software if it's not so obvious, but you can also just mathematically derive this without visualizing. Although I'm quite visual, so it helps me to look at the crystal structure along different angles to see what it is. Right. So we look at the lithium ionic radius. It's 0.76 angstrom, so that will fit. Now, then when you go and look at, let's say, sodium ion with the same charge, which is always +1 because it's alkali, right? But the coordination number, if it's the same coordination number of 6 for sodium, that's like 1 angstrom or 0.9, very close to 1 angstrom, right? So that's not going to fit, right? It's basically going to start exfoliating your graphite sheets, which is fine if that's what you want. And sometimes that's what people do want in layered materials. They introduce intercalants like molecules to basically break apart layered materials. And that's what you do in vaccines, right? You introduce intercalants and you can exfoliate and make high surface area materials. So it's not always that you don't want to exfoliate. It's just for this particular purpose, you do not want exfoliation, right? You want your anode material to stay intact. Anode in particular for lithium ion battery materials. So I want to be very specific about that because anode is a relative term, anode for what? So because if you're going to use lithium metal, I mean, graphite is higher in chemical potential than lithium, in which case that's the cathode if that's what you're wanting to do, right? But that's not the case here, right? So I try to be very specific. Even though I think it's pretty obvious when we talk about lithium ion batteries that graphite is often used as the anode. So then the next part, it goes into more the kinetics, but I just wanted to give an example of how understanding the crystal structure and doing characterization like X-ray diffraction while the battery is charging, discharging is very useful for understanding the insertion and deinsertion mechanism, because it's not always obvious, how these ions interpolate. So there are two models that are listed here, the Rudolph and Hoffman model, and also the Damas-Harald model, where you could see, depending on how many lithium ions you're intercalating, you have different stages, right? And so this has been studied quite a bit by a number of people. Well, the people created the model. So those papers are uploaded. So this has been known since like the 1960s, right? So this is nothing new. And also Jahn has, in his PhD dissertation in physics, has mapped out the phase diagram of lithium ion insertion into graphite. So this is pretty well understood since like the 60s, 70s, and 80s, although Jeff done his PhD in like 82. So it's been around for a while. But that's all to say, regardless of which model you follow, eventually you get to full insertion of lithium carbon 6, but along the way there are different stages. So there's a model that says, okay, well, the ions can intercalate and then they can order like so, right? So you can have stage 4. That tells you how many layers are between the ions. So here you see 1, 2, 3, 4. Okay, to go from this layer to this layer. So there's stage 4, stage 3, stage 2. So this mechanism is known as staging. And you see this in lithium titanium disulfide as well, where you use titanium disulfide as a cathode material. And in the early 80s, it was really the material to be studying. Jeff Dahn did his PhD, most of his PhD on this as well, before his work in NMC later on. But so you could see that, the ions can, from stage to stage, order, and then eventually, you have full filling like you see here. Or you could also have a staging model where you have ions that insert, but then the graphite layers can actually mold around each. So it's not as ordered, and they can mold around and be a little bit more disordered like you see here. But eventually they all, they all order where there's one layer of graphite in between the lithium ions. Okay. So this is all to say, if you understand the crystal structure, then a model like this can arise, and the fast ion diffusion will be in the layer, in the basal plane, as opposed to in between, right? Because even between these two models with the staging, you could see that it's going to be more difficult to have diffusivity or diffusion in the C-axis than in the A-axis, but that's because what the crystal structure of graphite looks like. Okay. Which extends to the argument of lithium polar oxide and similarly ion diffusion in R-bar-3M lithium cobalt oxide. Okay. Now, we talked very briefly about cubic structures, and if you wanted anisotropy, right? That you wouldn't pick a cubic structure, but that's a superficial, high-level statement. If you drill down to the crystal structure itself, and you have something that's polycrystalline, even though you have these channels in, let's say, another famous cathode material, lithium manganese oxide, where the lithium ions are these black atoms here, right? You clearly see there are channels. There's going to be a preferred direction for the lithium ions to travel, right? Because if it's going to, this is something we're going to talk about in the next module about ion conduction, right? If the ion conduction is going to be vacancy mediated or interstitial mediated, that means if there's a vacancy, if there's an empty site, that means there isn't a bond that the atom has to break in order to occupy that site, or there aren't as many bonds that it has to break, right? So that means your delta H is going to be different than if the site were occupied. Also, if the site were occupied, well, now you can't have two ions in the same site, right? So so the crystal structure will tell you, what the mechanism of diffusion is going to be, which affects, that's a physical property that we're interested in when we talk about energy storage materials. So one of the, lithium manganese oxide is of course one of the materials that's been heavily studied along with lithium iron phosphate, of course. But for this particular example, lithium manganese oxide, right? It has there are obvious reasons why people were looking at manganese as a replacement for cobalt, right? It's relatively cheaper. It's more earth abundant. So you see here manganese, if you normalize abundance of these atoms relative to silicon, right? Because sand is everywhere, silicon dioxide. You can see that manganese is more abundant than cobalt. So that's good. In terms of cost, I looked this up last week and you could see the huge price differential, right? It's a little bit more obvious when you just look at the metric ton. Okay, 2,000 per metric ton for manganese versus 33,000 per metric ton. But I should say cobalt prices go like this. You know, so last week it was like 80,000 per metric ton. 2018 it was 33,000 metric ton. But that's all to say it's still a magnitude difference than manganese. So even though the prices fluctuate like this, you know, the point is manganese is cheaper. So okay, so that's pretty obvious. But in terms of engineering this material for ion conduction and ion storage, you know, as an energy storage material, people have been looking at this since, you know, the 80s with not only electrochemical insertion, but also chemical intercalation. You can just stick this in and, you know, N-butyllithium and, well, not T-butyllithium, N-butyllithium and study, you know, just the possibilities, you know, the crystal structure changes upon lithium insertion. So if you download the crystallographic information file and you see, okay, well, it's FD bar 3M. So we see the D glide in there along the A direction, bar 3 along the 111 direction, and then a mirror plane along the 110 direction. And these particular directions are because it's a cubic material. Okay. So the last parameters are A, B, and C. Alpha, beta, gamma is 90 degrees as expected for a cubic structure. So then you look at, okay, well, the lithium ions are for this particular crystallographic information file, it's at 1/8, 1/8, 1/8. These are special crystallographic Wyckoff sites. Manganese is at half, half, half. Oxygen is at quarter, quarter, quarter. Although once you do the refault refinement, it's actually a little bit off. It's actually like 0.6, 0.26. So, so it's a little bit off, but for the purpose of this example, they made it a little bit more symmetric to quarter, quarter, quarter. So it's a little bit easier to visualize, at least on 2D. Once you download the SIFT, you can just rotate to your heart's content and find all of this. Okay, so right, so I went through and, you know, the viewing directions along A. So A is coming in and out of the page here. So if you look at the example of manganese at 0.5, 0, so I've highlighted that here. That if you do the D glide, right, you translate Y plus a quarter, Z plus a quarter, and you can generate the new atoms, the new manganese at 0.5, quarter, quarter. And then you could do this for all of the sites, all of the symmetries. And how many atoms of manganese do you expect within the unit cell based on this crystal structure? First option is to count all the atoms that are here, but you're going to be misled because it's a 2D projection. You can't see it all. Second option is to look at the multiplicity. Yes, specifically manganese. But you can also give me multiplicity for lithium or oxygen. Yes, you just read out the multiplicity. You read out the Wyckoff. Yes. So in the international table of crystallography, there's a reason why I just took a screenshot to be demonstrative. Right. that tells you how many atoms is going to be in the unit cell. So when you do all these symmetry elements, you can just say, well, did I recover all of them? Just count, right? You know. And why is it A, B, C, D? That's arbitrary. You start with A and then go to, you know, well, however many are in the international table. In this case, they went up to E. Okay. Now, why is there not B and C? You see some of these empty spots. They're just unoccupied. Okay. Okay. So then here I go through the example of bar 3 along the 111, the body diagonal of this cubic structure. So if I pick lithium at quarter, sorry, not quarter, 1/8, 1/8, 1/8, I rotate by 120 degrees, so the 3, and I invert. I get to this set of coordinates, and then the bar 3, that's inversion, so I put negative in front of everything. So that's fine, but then I now move it back to the original unit cell because I want everything to be between 0 and 1. So if I add +1 to negative 0.375, negative 0.375 plus 1, negative 0.875, I add 1, I get this. And so if you start off with this atom right here, lithium, you generate this atom. Okay. So I try to take a screenshot. So it's a 2D projection, but it should be obvious once you rotate in like Crystal Maker or Vesta or whatever your visualization software of choice is. And then the last part is the mirror plane. So M is going to be, there's a mirror plane along 110, which just went through that direction. So that's, this is A, this is B. So the mirror plane is going to be 1, 1. It doesn't, it's parallel with C, right? Because it's 0. So here's your mirror plane, which means this atom is mirrored there, this atom is mirrored there, this atom is mirrored there, and so on and so forth, right? So you can generate all the atoms in this crystal structure based on its base group. And there are 32 oxygens. Okay. Okay. Also, not surprisingly, the multiplicity also is in agreement with the stoichiometry. FYI. Okay. Okay, so what about the crystal structure? Well, okay, you think, well, I see a channel of insertion and deinsertion. That's pretty good. If it's a polycrystalline powder, even though it has anisotropy, you know, the crystals are going to be oriented in whichever direction. So it's going to be sort of a wash unless you're designing a thin film battery for the Internet of Things application, and you want to put it in a like a wearable watch or what have you, you know, okay, fine. Then you can orient this crystal and you can grow it in an oriented direction. That's totally fine. But in polycrystalline material, even though it's anisotropic, all the crystals are going to be pointing whichever way anyway. Okay, so then you think, well, it's a cheap, manganese is cheaper. You know, I can control anisotropy, I can control diffusion, direction. Well, what could possibly go wrong? Well, then you have to connect the chemistry to the crystal structure. And this is where things start to break apart a little bit. And this is where the engineering comes in. So you combine material science, a little bit of engineering, a little bit of chemistry, and then you start to understand why this material is going to destabilize at high voltages. Okay, so a review, although I think this side of the room sees this all the time, given their educational background, but for review, for 3D elements, we're going to focus on manganese. So the redox couple, when we went over the example of lithium co-1 oxide, we talked about cobalt going from 3+ to 4+, and that is the redox couple. That is the mechanism of charge storage, right? Lithium is +1, it goes to +1. Nothing changes there, but it's the transition metal that is the redox couple. That is what goes through reduction and oxidation, right? So in space, a 3D metal, all the 3D orbitals will be degenerate, but we're not in space, we're not in vacuum. There is there are ligands. So these are oxygen. Those are the orange atoms here. Lithium are in these tetrahedral configurations. Manganese is in the octahedral. That means there's 8 sides, right? Six-fold coordination. So in these configurations, if you have manganese surrounded by the 6 oxygens in an octahedral environment, you get this Jahn-Teller distortion where the 3D orbitals are no longer degenerate, right? They go into an EG and a T2G energy level, so they split. Manganese in this configuration is a +4, so Mn is +4. So that means then that there are three electrons, right, that are going to occupy these orbitals. And of course, according to Hund's rule, right, that they're going to occupy 1 per orbital in the lower. So you build up. Okay. So, okay, that's fine. Now, what happens when you go through the redox couple and manganese becomes 3+? Well, this configuration is, well, there's 1 extra electron, and the configuration is going to be now tetragonal. It's no longer just going to be this in this octahedral environment. So in fact, the orbitals will split again. So the EG will split again, T2G would split again in this particular tetragonal symmetry. And there are 4 electrons, so you fill it up, 1, 2, 3, 4. Okay. But then you think, okay, well, it has to go from this symmetry to this symmetry. So it goes from cubic to tetragonal. And so now we go back to thermodynamics and we see that, right? So we measure the voltage, we go back to thermodynamics, there's a phase transformation, the Gibbs free energy has changed, and we see exactly that in the drop off right here, okay? And so let's review. When we see a plateau, that's indicative of a 2-phase coexistence. So when cubic goes over to tetragonal, both phases are coexisting, right? And the Gibbs free energy has lowered quite a bit. So the voltage you can see here is also decreased by a bit for the tetragonal versus the cubic region that you see here. Okay. So what's actually happening within this material, right? So not only is there, this phase transformation, but there's also 2 plateaus that you could see here. So the lithium ions occupy the tetragonal A sites, which we already saw that in this structure here, right? So that occupies these tetrahedral sites. I said tetragonal, sorry about that. I meant to say tetrahedral sites. And then in the second plateau here, but I should say, when I say X, I should denote that the nomenclature is actually this. And I write it like this for historical reasons, because John Goodenough has already done the study, and the way he writes it is actually 2X. So this, so when I say X, I really mean like X is 0.5, which really means it's already lithium 1, because it's 2 times that. And I try to stick with historical references so it doesn't get confusing, although, most people would just write LIX, but, because that's what we're all used to seeing. But this denotation is from John Goodenough, so I write it as Li2X Mn2O4. Okay, so when we see this and we say, okay, well, this is obviously different from when we discussed layered materials, the example of lithium cobalt oxide, right? We see sort of like a sloping, but really mostly a plateau, but still a sloping feature in the voltage. Clearly, this is not the case, right? There's a phase transformation here. So what it's saying is, for this particular material, you're limited if you don't want to go through this phase transformation, which could be obviously disastrous once you pass an electrode, right? It's in one crystal structure, and then you have a phase transformation you're going to mess up your electrode, right? And you're going to have volume expansion, your electrode is going to crack. You know, it's not going to be engineered in the way you have designed it from the beginning because there's a change in the crystal structure. So you're really limited to 1 lithium ion per 2 manganese cations. And that's different than lithium cobalt oxide, because then there you have a 1-to-1. You have 1 lithium to 1 cobalt, right? So in terms of engineering, the fact that there's this phase transformation all based on the crystal structure, the manganese surrounded by oxygen, right? In this symmetry, the cubic going to tetragonal is the reason why manganese is not a stable, lithium manganese oxide is not stable unless you limit your window, your operating window versus the voltage or capacity. I mean, they're both related, right? So you can just cycle between here and let's say maybe here, and that's fine. You know, you get this amount of capacity out and that's fine, but that's your limitation. It has to be, it goes back to the crystal structure. Okay. So to give you some perspective, you know, just because manganese goes through, lithium manganese oxide goes through phase transformation, doesn't actually mean it's that terrible, because it allows us to understand what we can do to engineer a material that is stable. So, oh, okay, oops, sorry, we're 2 minutes over. So I'm just gonna wrap up, but I'll continue here because I wanna make, you know, a specific point, which is, it's okay, you know, we can understand that manganese 3 is unstable in the tetragonal, in the tetragonal symmetry, but we can say, okay, well, if manganese 3 disproportionates into manganese 2 and manganese 4, is there another transition metal that's in the 2+ state that we can use to stabilize it? So we can basically reduce the amount of manganese 3 content in the spinel structure. And the answer is nickel. And Jeff Donnery figured that out, hence NMC. You're welcome, world. And that is the reason why you have nickel substitution. It's to stabilize the manganese 3. And so hence NMC, also substitution of nickel into lithium manganese oxide, and then also lithium excess type materials as well. So understanding this and the failure, okay, I wouldn't say failure. It just, the destabilization of manganese 3+ leads to, okay, leads to engineering other stable, highly commercialized materials these days. Okay, with that, thanks everyone. I'll wrap up here. All right, let me.